let me just warn you guys in advance that our next door neighbors, we're in a townhouse here, and so we share a wall with our next door neighbors, and they have begun a bathroom remodeling project. So there may be a fair amount of extra noise here. I'm gonna have to look into buying a separate microphone or something like that if the noise gets too bad. But please, if there's too much noise and you can't really hear what's going on, just raise your hand or yell out something and I'll try to clarify. All right. There, that was some drilling. I don't know if you heard that. All right, well, we have not so many participants today. Are people losing interest in these Zoom meetings? I do see that a bunch of people are looking at the recorded versions, which is fine. But this is your chance to get questions answered. So, do you have any questions that you need to ask me about the homework that you've started to work on? And this new material is now about these path integrals, well, we'll be doing surfaces today too. Any starter questions? All right, well, I had a little extra time while I was getting rolling this morning, so I actually prepared a few slides in advance for you. We'll try to get slightly better artwork today. So let me spin this around. And get some good visuals. All righty. So when we last left our heroes, we were discussing integrals, and I remind you of the general pattern for how integrals are always defined. It doesn't matter what function you're integrating, it doesn't matter what set you're integrating over, it's always the same general recipe. And I tried to clarify this in a new setting last time, where my set S was some sort of wire that wound through 2- or 3-dimensional space. And the function that I had in mind was a function that would represent the density of the wire in, let's say, grams per running centimeter. So that allowed us to compute something which I claimed would actually represent the mass of the wire. And my reasoning was very simple. You would take the wire and split it up into a lot of pieces. And you would, on each one of those pieces, you would figure out the density in grams per running centimeter somewhere within the wire, that little piece of the wire rather, and multiply it by how long that piece was. That product would measure the mass of that piece. Obviously, if you add that up for all the pieces, you would get the total mass of the wire as you have split it. Of course, it's all just an approximation because the density could be changing even within a little piece. But in the limit, as the pieces grow tiny, then this sum will get better to become a better and better approximation for the total mass. Now, another illustration of this concept of what integrals can do, when you take this definition of an integral, you realize that in the special case that the function that you're integrating is constant. Let me pull this a little closer for you. If the function is constant, then every time you look at the value of the function on a piece, you'll get the same exact number, c. And so you'll be having c times the sizes of the pieces. If that's a constant, you can pull it outside of this sum. And again, if it's a constant, you can pull it outside of this limit. So all you end up with is c times the limit, as the pieces grow tiny, of the sum of the sizes of the pieces. Well, when you add together the sizes of the pieces, you just get the size of the whole set. It doesn't matter when you take a limit or not. The sum of the sizes of the pieces is the size of the whole set. And in a very special case, when that constant is 1, you see that integrating the constant function 1 over a set S just gives you the size of the set S. Size will mean different things in different contexts, but in the case where your set is just an interval, then the sizes of the pieces And the sizes of the overall set just mean the lengths of those pieces. And sure enough, if I ask you to integrate the constant function 1 over between x equals a and x equals b, I know a lot of you would take the antiderivative, which is x, and stick in x equals a and x equals b, and when you evaluate, you'll get b minus a, but that is in fact the length of the interval. We've already had a few other problems where the set that we were splitting up was a portion of the plane, and then our notion of size meant area, so we were computing the area of a region in the plane. And I think we had some as well where you were computing the volume of a set in three-dimensional space, but it's the same principle. In this new chapter now, we're also looking at the case where we're integrating over a curve, and then when you split this up into pieces and ask for the sizes of those pieces, the size of a little portion of this curve should only be interpreted as the length or arc length of that portion of a curve, and then what the integral is giving you is the overall arc length of the whole curve. So I want to do some examples today where that's exactly the question, is how long is a curve where the curve winds through 2- or 3-dimensional space. So that's fine as far as the interpretation of this thing goes, but we do have this question of how exactly are we going to do the computations? I mean, along the way, how are we going to measure the size of a piece? And for that matter, how do you split the curve up into pieces in the first place? And I indicated last time how we would do this is what we end up doing is we just parameterize the curve. So I'll have phi be the name of a parameterization that goes from R1 into R2 or R3 in such a way that this function phi will map an interval in the real number line into the curve that we were given in 2- or 3-dimensional space. And I've even indicated how I'm going to answer this question of how to split the curve up in the first place. Once you have a parameterization, then the natural thing is to split this curve up into pieces, just split the interval up into pieces. Then you watch where each one of these little intervals gets carried in 2- or 3-dimensional space. And that gives you little arcs there. And when you have to select a point inside each one of those pieces of the curve, well, the easy way to do that is just select a point in this little interval that's back here in the real number line and figure out where phi takes that one point. And that'll be one point inside this little arc, or the next, or the next. Same thing here in 3-dimensional space. And since I want to start working on surfaces today, let me say that the same thing is going to be true, the same answer is going to be true for surfaces. If you need to parameterize, if you need to split a surface up into chunks and compute the sizes of those chunks, what I'm going to encourage you to do is to find a parameterization of that surface using some portion of the plane. So you'll have a function that goes, the function capital T that goes from R2 into R2 or R3, and you'll find a set in this copy of R2 over here. I've drawn it as a rectangle, but it doesn't necessarily have to be just a rectangle. Any set that's reasonably easy to work with, if you find a parameterization that carries a reasonably nice set here onto exactly the patch of space that you have to integrate over, well, then it's easy to partition that set. You just partition this set and watch where each one of these little pieces goes under the transformation capital T. So I've drawn it, this is a 3x4 rectangle here. It's divided into 12 little pieces, and each of these is correspondingly now divided into 12 little pieces. And when you have to pick a point inside each one of those little pieces, obviously the way to do it is just to pick a point inside the smaller piece that corresponds to it. Now, we have already been looking at this portion of the picture, of my big scheme here. This is what we called the change of variable theorem before. But after we got used to dealing with the change of variable theorem, I started to whisper that actually what you are doing is parameterizing this surface with a simple surface in the plane. It didn't really feel too much like a parameterization because you went you were in R2 in the first place, and you were parameterizing it with a different subset of a different R2. But we're going to deal with surfaces that float around inside R3, and then this really does feel like a parameterization. You'll have a function that maps pairs of numbers onto, well, these will all be points in three-dimensional space. They'll all have a triple of x, y, and z coordinates. So that'll be what we would call a parameterization, something that gives x and y and z as functions of just u and v. I guess I should start to label my axes. We use t as the name of our parameter in the one-dimensional setting, but typically in the two-dimensional setting, they might be, well, s and t, or u and v, or something else. But these are mapping into either the xy plane or xyz three-dimensional space. So you have to give each of the output coordinates as a function of the input coordinates. So that gets us past this question of how we're going to split sets up in the first place. Is after we have a parameterization, we just split up the domain of our parameterizing function. But then when you do that, you still have the question of, yes, but how big exactly are these little pieces that you get by applying phi to a little interval in the real number line, or by applying capital T to a little, let's say, rectangle in the UV plane? You're not getting rectangles anymore, and so it's not clear exactly what the area of the outputs would be. And I told you last time what the answer would be, but I didn't really clarify it. I just called it a fact, and then I ran with that. But I want to spend a little time today showing you why that fact works. So here I've taken a magnifying glass to a portion of this picture. I'm zooming in on the little interval, a little interval that's in the middle of this big interval here. And supposedly I have this parameterization function phi that will carry this little interval to some twisted interval in the plane or in three-dimensional space, I don't care. And I want to ask the question of how exactly am I going to get the length of this curvy thing over here? I mean, that's kind of reducing us down to this question again, but if I don't know how to compute integrals on curves, it feels like I'm not really making progress. But in the case where this interval is really small, I'll be able to get a good sense of how big its image is as I apply the function phi. I mean, you know that phi is twisting these parts of the real number line around and giving you, well, there's still curves over here in this new picture. But if this interval is small enough, then the function phi doesn't have much chance to twist this into something that's too wild. See, in the big picture, you can get a lot of twisting. But if you only apply a function to a little interval, then you don't expect its image over here to twist by very much. Well, I mean, it can. In the mathematician's zoo of wild functions phi, you can have a function that manages to twist even tiny little intervals into a lot of junk. But for us, we're taking the sort of nice functions that you see in a science and engineering setting. Specifically, we call them the differentiable functions. And in that case, we can see pretty much how long this arc is from the left-hand edge to the right-hand edge. If I'm going from T1 to T2 in the domain, phi will carry that to an arc that connects phi of T1, that's this point, to phi of T2, which is that point. And the length of this arc will not be very different from the straight line segment that joins them. It will not be very different from the distance between the two outputs, phi of T1 and phi of T2. That's where I'm using the fact that that this interval is very small and phi is, well, continuous. Unfortunately, I don't exactly know where phi of T2 is anyway, and I don't know how I would compute that distance, that length. But this is where we had the idea from differentiation earlier in the semester. The whole point of differentiation is that it gave us a way to approximate what happens to a function phi when you change its input by a little bit. I've called the vector that goes from t1 to t2, I've called that v. So for us, that's just a little arrow in the real number line. But you're applying the function phi to this point t2 to figure out where this point is. And so I need a formula that tells me how to estimate phi of t2. Approximately, where is that point? So how do you apply the function phi to a point that's a small displacement away from your starting point? And what we said early in the semester was that that will be approximately the same as the point phi of t1. However, it's moved a little bit away from phi of t1. So this point will obviously not be quite exactly where this point was. But the vector of displacement in this picture can be found by multiplying the vector of displacement in that picture by this matrix that describes the linear transformation. It's the best linear approximation of the function phi in this region. So that was the point of this derivative. I asked you guys to start thinking about phi prime of t1 as being a matrix. It is a matrix that's representing a linear transformation, a linear stretching phi, or stretching or rotation or something. But it's a matrix that transforms small vectors in this picture to small vectors in that picture. So this output vector that I've computed over here would be, you're multiplying a matrix times a vector. Now I say matrix and vector, although in this case a vector in R1 is just a small, it's a small number really. And this matrix in our setting, let's see, if phi goes from R1 into R2, this is a 2 by 1 matrix, so it's just got a single column. And I'm multiplying that column by a small number in the real number line, and that'll give me a small column. But that column tells me how far away this point is from this little star. The little star is not exactly where this second dot is, because this was only an approximation at this stage. The star, the location of the star, is what you would get by starting at phi of t1 and moving by this vector here, that moves you away from phi of t1 to something that's close to phi of t2. But now my thinking is that the length of the arc is almost the same as the length of the straight line segment that goes from phi of t1 to phi of t2. And the length of that straight line segment is almost the same as the length of this straight line segment. The length of this vector that goes from phi of t1 over to where the little star is. And the length of that vector is this thing. It asks you to compute the length of the vector that you get by multiplying this matrix times that vector. And as I say, in our setting now, if this is a 2 by 1 matrix and that is a number, then the length of that vector will be the length of the single column phi of t1, phi prime of t1, multiplied by the length of the vector v, which is just the length of the interval on this side. So here's where you end up with the fact that I gave you last time. I've just proved this fact for you. What I told you last time is that what this phi does is it stretches the lengths on the left-hand side to become the lengths on the right-hand side, at least approximately. And our formula is that the length of this little piece of the arc, the length of little piece of this curve that I split up in the first place, is stretched by phi by a factor of this number right here. It's the magnitude of this vector phi prime of t evaluated at the point t1. I mean, as you move from left to right in your integration problem, you're splitting your interval up into lots of little intervals. The amount of stretching could be different here from what it is on the next interval and the next and the next. So that's why there's a T1 in here. This phi prime will vary as you move from little interval to little interval. But in every little interval, this would be the fudge factor that tells you how much lengths are stretched. So with that in mind, when you go to compute the integral of a function over this arc, you know you want to write it as this limit of sum of values of the function of f times the sizes of the pieces. But the sizes of the pieces in the curve are the same as the sizes of the little intervals in the left-hand picture multiplied by this fudge factor, which has to be evaluated somewhere inside that interval. So that's what all of this turns into. And then you still are supposed to be evaluating the function f. I'm supposed to evaluate the function f on these little circles, but the way I got those little dots was to apply phi to the points that were in these little intervals. So I'm evaluating the value of f composed with phi on the little interval, somewhere on the little interval. And those are the things we sum over all the little intervals in the domain, and we take a limit as those pieces get tinier and tinier. And so I am re-evaluating this integral as a very similar kind of expression, but there's some references to phi in here. And then that's when I realized that all I've done is I've chopped up the interval in this picture into little pieces. And then I multiplied the sizes of those pieces times the value of this function, which is to say I'm integrating this function on the interval in the real number line that I showed in the picture, in the t domain. So I'm showing you how to integrate a function over a curve by instead integrating some other function on an interval. All right, now, all of that is fine. It sounds like we're making progress because we know how to integrate functions of one variable over an interval in the real number line. The difficulty is that all of this begins by having a parameterization. So I'm going to give you a very specific example and we'll see how we would make this work in practice. So I would like to look at the curve of points that have y squared equals x cubed. And that includes 2 points that I know of. One is here at the origin and the other is here at the point 1, 1. But somehow this curve makes its way from one of those points to the other one. I don't quite know what the picture is just yet, and I'd like to figure out the length of this curve. All right, well, everything we've done so far today says you should be able to get the length by simply integrating the number 1 over this curve, whatever it looks like. And then what I proposed doing in all of these calculations was that I can evaluate the integral of any function over any curve by going through this process where phi is a parameterization of the curve. I'll be integrating, well, the constant function composed with phi. That'll actually just turn out to be equal to 1. But then I'll have to multiply that by the magnitude of the derivative function. And I'll integrate that with respect to t over the interval of t's that I need to parameterize the curve. Yeah, that's great, except I don't know what this interval is because I don't know what this function phi is. So this is why I worked with you guys earlier in the semester to think about the 3 ways that you could be presenting any geometric set, including any curve. You could give it to me, well, we want to get it parametrically, but we also can have the curve presented either explicitly or implicitly. Well, which of these three ways do I have in the first place? Which is the format in which this curve was given to me in the original problem?
Implicitly?
Yeah, it was given implicitly because you see one equation linking the two unknown, the two coordinates, x and y, that every point will have. This is our membership test to decide whether or not a point is in this curve. Or to say it in the kind of language you had earlier in the semester, here we had a function of two variables. Let's take the function y squared minus x cubed, and we're setting that function of two variables equal to 0. So this is a level curve of a function of two variables. Here's the function that went from R2 to R1. So in order for us to make some progress, we have to present it parametrically. Well, how do we take a curve that's given implicitly and rewrite it as a curve given parametrically? One of the ways that we've decided that you could go this way in the picture is to make a roundabout route by going there and then here. How could you present the same curve explicitly? To give it explicitly, you want to be giving it as the graph of a function of one variable. So this would be a function that went from R1 to R1. What function is this curve going to be the graph of? How did we do that? How did we transform a curve from being given implicitly to being a curve given explicitly?
Solve for x.
Yeah, solve for, well, you could solve either way. You could solve for x or solve for y. But right, the point is to express one of the variables as being a function of the other variable. I guess for curves in the plane, most people are expecting to give y as a function of x. So take this equation and solve for y. So your presentation now would be y is equal to x to the 3/2 power. So what's the point of this? Well, the point of giving it explicitly is that if you have any curve that's given explicitly, then you could give it parametrically as well. To give it parametrically means you have to give the kind of function we were discussing earlier today. I need a function that goes from R1 into R2, and I want the image of this function. I want to have a function that presents x and y separately as functions of t. So I have two outputs from the one input. And when you have a curve given explicitly, you have an easy cheat. You can always just take x to be the same as t. And then y would have to be whatever function of t this expression dictates. If x is the same as t, then you just need y to be t to the 3/2 power. So this is one way that I could get a parameterization of my function. And you can chart exactly what range of t's you need in the parameterization. If the t's and the x's are synonyms, then the range of t's that would parameterize the set will be the same as the range of x's that you have when you think of the curve this way. In other words, if you think of this as the graph of a function, tell me the x's that you're graphing over. Tell me, just project down here to the x-axis and tell me the range of x's. And as you can see in this picture, you have x's that go between 0 and 1. So you need t's that go from 0 and 1. So the parameterization that we're going to use will be phi of t is t comma t to the 3/2. And then my interval, my domain here, is we are going to use the range of t's that goes from 0 to 1. So this allows me to compute the length of this curve as it's now an integral over the interval that goes from 0 to 1, or if you want to do it in Calc 1 terminology, it's the integral from t equals 0 to t equals 1 of, so for lengths, I don't need to put in this factor of a 1. 1 times anything is unchanged. But then what will go in here will be the magnitude of this vector, the vector that is the derivative of this expression. If you want to use the matrix terminology that I had before, it's a column vector. It's two components in a column. First, you'll have the derivative of the first output variable. Underneath that, you have the derivative of the second output variable. Or you could just think of this as being an output location and then its derivative. If this is your position at all times t, then what I need is your velocity vector, which is the derivative 1 comma 3 halves times t to the 1/2 power. And that's what you'll integrate with respect to t. And you know how to compute the magnitude of a vector. It's the square root of the sum of the squares of the two components. So this is what I would have to integrate, and I do that between t equals 0 and t equals 1. You can finish this quickly with a u substitution. Let u equal 1 plus 9/4 t, so that du would be equal to 9/4 times dt. And then my integral is now written as the integral as u goes from 1 up to 1 plus 9/4 will be 13/4. And my integrand is just u to the 1/2. My differential is going to be 4/9 of du. And this is now easily computed with the fundamental theorem of calculus. I'll get u to the 3/2 times 2/3, evaluated between u equals 1 and u equals 13/4. So with a little bit of arithmetic here, I get 8/27 times 13/4 to the 3/2 power minus 1. I think I did the integral correctly. I'm actually not too concerned about this part, but I do want you to see this part. The point of all of this is that I was able to compute the length, which I knew could be thought of as an integral over a curve, but I changed it from being an integral over a twisty curve into an integral over just an interval in the real number line. And that's true for any curve as soon as you can parameterize it. Now, just for reference, I'd like to show you another parameterization you could have used for the same curve here. When you say that you want to have y squared equal x cubed, and you think about each of these two coordinates as being the outputs, where'd it go? Both the x and the y coordinates were given as functions of t, separate functions of t. You need to think about what functions of t, two functions of t you could write in here. Oh, sorry, this should be called phi2, such that the cube of the first function of t matches the square of the second function of t. And that's not an obvious thing in general. If I give you some weird equation with x's and y's, there's no easy trick that lets you parameterize that. But in this case, you might observe that you could have phi of t be the following pair of functions. How about if you put t squared in this spot and t cubed in that spot? Then the cube of the first function matches the square of the second function because they're both going to be equal to t to the 6th. And you can tell what range of t's you need because you need, first of all, for this expression to match the pair 0, 0, and that will obviously happen when t is equal to 0. And later you need this pair to match the pair of numbers 1, 1, which will happen when t is equal to 1. So in this case, I would say that I'm going to use this parameterization on this interval. It happens to be the same interval, but that's just a fluke. But now here's a function that carries this interval onto this curve. And so my length can now be found by integrating the magnitude of the derivative of this parameterization function, again on the interval from 0 to 1. And this integral looks different because my parameterization is different. I'm integrating from 0 to 1, but this will be the square root of the sum of the squares of the derivatives of those two component functions. There's a 2t for one and a 3t squared for the other. So if you try to evaluate this integral, you'll see that you have a factor of t squared dividing both of those factors, both of those summands, you could factor that out and then bring it outside of the integral sign. So this would be what would remain from that. After I pull out the factor of t squared, what remains here is a 4 for that one and a 9t squared for that one. So the integral looks very different, and that's not a surprise. Anytime you have a radically different parameterization, you should expect to see a very different looking integral. And as a hint, then, let me tell you that that could work to your advantage when you need to calculate an integral over a set. If you chose a parameterization and you're getting horrible looking results, see if maybe there's a different parameterization that would turn your original integral into a very different looking integral it's over some interval in the real number line. I'll let you finish this if you want. Obviously, to compute this integral, you might let u be 4 plus 9t squared. You see most of your du showing up in there. So then you would end up with a square root of u, kind of the same as in the previous problem, but some of the parameters of the problem would be a little different now. You will get the same number. You know you have to get the same number as the answer because you're computing the same quantity. Intrinsically, this was just the integral of 1 over the curve. So that's it. That's path integrals. That's all you need to know. The concept behind it is always clear. Integrals always mean the same general thing, but the method of computing them is always going to be the same. You're always going to look for a parameterization and then evaluate this integral over an interval, and that'll give you the same as the integral of the original function over the original curve. Comments or questions about those path integrals? Let's make sure you're okay with that setting, where it's curves in the plane or curves in three-dimensional space. Okay. You'll find that people often break out separate cases when the curve is given explicitly or when the curve is given parametrically. They're not really separate cases. Sometimes people want to make it a separate case where the curve is given in a nice explicit way, but you know that you can turn it into a parameterization by using the little trick that I had right here, and it will turn into exactly the same kind of work that I just did. I would encourage you not to think of those as special cases unless your memory is really good and you can memorize separate formulas for some of those separate instances. Now, let's talk about integrating over surfaces. So what about when you have to integrate over some sort of a surface that floats around in three-dimensional space? I give you some function. Let's suppose that the function has been described in terms of the x, y, and z coordinates of a position. So nominally, this means you're going to take your surface, think about it as a waving flag, and you chop it up into some little pieces. And on every one of those pieces, you evaluate the function somewhere inside the little piece. You multiply by the size of the piece. Okay, I think we would all agree the size of a piece should be thought of as the area of that piece, if you could somehow flatten it out. And then you add up those products, a value times an area. You add them up over all the little pieces. That'll be approximately what you're trying to compute. Of course, you take a limit when the pieces get smaller. So how are we actually going to evaluate this? How do we go about splitting this thing up into little pieces? How are we going to evaluate the sizes of each of those little pieces? And I said over here, the answer of the trick that I'm going to recommend is that you parameterize your wavy surface by finding some, preferably a nice simple region inside a two-dimensional space. Give me a parameterization that carries that chunk of the plane up to or over to this portion of three-dimensional space. Obviously, if you do that, it'll give you a way of partitioning the surface. You just partition this portion of your domain. And it gives you a way of selecting a point inside the little patches. You just choose a little point over here to evaluate. And if you want to evaluate a function f on one of these spots, you just say to yourself, well, I'll take this starting point. I'll first apply the function capital T that'll carry me to that dot, and then I'll evaluate the function right there. So I will effectively be computing f composed with capital T. I'll be evaluating that function on these dots. The missing ingredient is I got to know how big these little pieces are, and somehow I know that they're related to the sizes of these pieces, but I don't know how this function capital T is going to mess things up. It'll obviously be stretching or shrinking the areas in some way. All right, so that's really the question. So let me put another magnifying glass over this, just one of these little rectangles in the UV plane that makes up my, my original shape. So I had taken my original shape, which I represented as a rectangle, and I divided it up into lots of little pieces. But if I zoom in on one of these little pieces, how am I going to visualize what the sizes of things are? So here's one little rectangle that goes from one point, P, and it stretches a little bit in two directions. So there's a vector that goes this way and a vector that goes that way. So let me call these vectors, I don't know. Well, yeah, I drew this as if it were part of the UV plane. Oops. So how about if I call this little vector here du? I've moved a little bit in the u direction to move from the point P to a nearby point, which, well, you take the point P and you add to it this vector du. So I'm going to emphasize right now, I'm thinking of this as the name of a vector. And this is adding a vector. This is a displacement vector away from the point P that gets me to this other point. You want me to call it Q? And likewise, I could have another different small vector, dv, that would take me from the point P to another vector, to another point. I'll call that r, but it would be calculated as P plus dv. And I'm thinking of these things as being vectors now, but if you want to write them out in a vector form, usually you write a vector as being, you know, a pair of numbers stacked up on top of each other or with pointy brackets on the sides. So really the way I should write it is either the pointy bracket notation or the column notation. And well, if I draw these little vectors parallel to the axes, then I think it's clear how they're supposed to go. This dv, for example, it moves no units left and right, but a small number of units up and down. Or if you write it as a column, it's a 0 on the top line and a little number dv on the bottom line. Same thing over here. I shouldn't write it as p plus, I mean, I'm using du as a vector in this setting, but let's start to use it just as a number. So the corresponding vector would be, you go a small amount left and right and no amount up and down. And in the column notation, that means you're writing it this way, du on the top number and 0 on the bottom number. All right, so what does my transformation capital T do to this? Well, again, it's mapping all of that pretty region of the UV plane into some sort of twisty region that's going to get divided into a lot of twisty pieces. But if I could just zero in on this region, let's see, where does the point P go? It'll be sent to the point capital T of P. And then this little line segment will be sent over to some curve that carries you to capital T of Q. And this little line segment will be sent onto a different curve that goes to this point T of R. For that matter, there's another corner that can be joined to these other two things, and so you'll get something that looks like a sort of a wavy rectangle. Now what I'm going to do is to say, you know what, why don't I figure out approximately where TQ is by using derivatives, and I'll get a point that I'll just call Q prime over here. That'll be almost the same as T of Q. And likewise for this, I'll get a point that I'll call r prime. I'll use derivatives to estimate approximately where t of r is, and I'll call that r prime. And then I'll replace these curvy things that really go from t of p to t of r with just a straight line segment that goes from t of p just to r prime. R prime is that dot. Maybe I should use little stars like I did in the previous picture. There's a star as well. And likewise, I'm going to replace this curvy thing with just a straight line segment. And you could even figure out approximately where this fourth corner goes. But what you would find when I use the first derivative method, I'll show you in a second, that will be actually a fourth corner of a parallelogram. And so here's my, my observation is that I should be able to get the area of this little piece that's shown in that picture, the curvy one, should I say curvy piece. That's going to be approximately the same as the area of the parallelogram that goes from TP to this thing that I'm calling Q prime to the thing that I'm calling R prime, and then finishing off with a parallelogram. So what exactly do I mean by these, the Q prime and the R prime? Here again, I'm going to use the formula that puts derivatives into this. That, when you want to compute T of Q, what you do is go back to this picture and say, well, Q is P plus a small displacement. It's P plus this vector. So it's P plus a little column vector that I'll write as du on the top and 0 on the bottom. And our sense of approximations from the first half of the semester is that this will be the same as the point TP plus a small displacement vector that's called T prime of P, that's a matrix, multiplied by this column vector, du on the top and 0 on the bottom. And the same thing if you wanted to estimate, so this is the thing that I'm calling Q prime here. Q prime is my estimate for the actual position of where Q gets sent. And it is exactly where T of P is plus a small displacement vector. So this is the little vector that runs along the bottom edge of this parallelogram. This vector right here is the same as what you get by multiplying this matrix times that vector. And in the same way, the other corner up here, T of R, is approximately the same as T of P as well, but there's a different displacement vector that'll get me there. I'll take the same matrix and I'll multiply it by the vector that's got those two components. So this is what I'm calling R prime. It's almost where capital R got sent. You start exactly where P got sent, but you go along this far. You take this much of a vector that takes you away from the point T of P. All right, guys, so now the question is, how do I get the area of this parallelogram? The area of the parallelogram, I should be able to compute that if I know exactly what these two vectors are that go along the two edges. And this is one of those topics that we had in the beginning of the semester as well. The area of the parallelogram can be computed from the two little vectors that join along this edge and along that edge. The area of the parallelogram is the magnitude of the cross product of the two vectors along the edges. I bet you didn't think you were going to see that formula again. So I need to take the cross product of these two vectors and find the magnitude of that vector. And that's made just a little bit easier by the fact that I know that these vectors are pretty simple. They're a constant multiple of 1, 0, and a different constant multiple of 0, 1. So this area is going to come out to be these two multipliers. I'll have a du and a dv, and then what's left will be, I need to take the magnitude of, the cross product of first this vector and then this other vector. And if you remember what happens when you multiply a matrix by these special vectors that have just zeros and ones in them, what you will see is that this is giving you the first column of this derivative matrix, and this one is the second column. But if you remember how derivatives were computed, well, how do you get the derivative of a function that goes from R2 to R3? That's a 3 by 2 matrix whose first column just consists of taking all of the partial derivatives with respect to u, and the second column consists of taking all of the partial derivatives with respect to v. So that, finally, is my formula for how we compute the fudge factor that'll say how much areas get stretched. You'll take the area of this region, which is exactly the number du times dv. That's the area of the little rectangle in the domain space. When you carry it over with capital T, there's a couple of things that have to be approximated. I'll replace this true point T of R with T of R with R prime, and replace T of Q with Q prime. They're almost the same. I'll further replace the curvy little patch with a parallelogram patch because, again, they are almost the same. In the limit, the differences will go away. And then the last step is to know the area of that parallelogram, and that is given by exactly this process. You take the derivatives of your parameterization function. It'll be a function of u and v. Take the derivative with respect to u first, and that'll be a column vector with 3 components. And the derivative with respect to v after that, that'll go in the, that's another vector of 3 components. The cross product of those 2 vectors is another vector whose magnitude is exactly the fudge factor that we need. All right, I was hoping to do an example, but I see I'm already 3 minutes over. So,
Professor?
Yeah, please ask.
Sorry, how did you get the vectors from TP to TR, I mean TP to TQ and TR? How did you get those 2 vectors?
How did I figure out how long that vector was?
Yeah.
That's me using this, this formula from the first half of the semester. If you want to figure out exactly where T of Q is, I can't tell you exactly, but I can approximate it. Since you are evaluating your parameterization function T, at this point that was close to P, I mean, this whole little picture is supposed to be really small.
Yeah.
You write that second point Q as being P plus a small displacement vector. This is your small displacement vector. And that small displacement vector has got this small number as its first component and a 0 as its second component. So now you realize you're asking us to evaluate T at a point which is a small displacement vector away from P. And our definition of derivatives at the beginning of the semester was that the first derivative is exactly the matrix that transforms a small displacement in the domain to a small displacement in the codomain. If you started off close to P, of course you expect to end up close to T of P, but you're displaced away from there a little bit. Exactly this edge, this displacement vector, is computed by multiplying this matrix times the vector of displacement you had in the first place, in the domain, I mean.
So TP itself is a vector.
No, that's a matrix. This is a matrix.
No, what TP, so T prime,
oh,
T
sorry,
prime P.
I'm sorry. Yes,
Yeah,
T of P is, well, T of P is a point in 3-dimensional
okay.
space.
I'm just wondering how you get a vector from that. But I guess the matrix, when you multiply it, turns into just a column vector. So
yes, this is a 3 by 2 matrix. You multiply it by a 2 by 1 matrix, and what you get is a 3 by 1 matrix, which is to say it's a column vector. And
okay, yeah, that's
your displacement vector.
Thank you.
Yeah, I wish we had time to do an example in full. You can find them in the book, but I'm going to do them with you on Monday. But I wanted you guys to see that this is where the fudge factor comes from. And by the way, if you carry all of this stuff out in just 2 dimensions, this will turn into the determinant of the Jacobian matrix. This gives you an alternative answer to the question of why does the determinant of the Jacobian show up in the change of variable theorem. It's because we're just carrying out all the steps that I just did, but with that kind of a picture instead of this kind of a picture. Go through it and you'll see that this ends up being exactly the determinant of a 2x2 matrix. Anyway, we'll do that together on Monday. Try some examples, stay ahead of the reading, stay healthy, and I'll see you again in a few days.